Warm greetings and very good morning to everybody. Today I'm going to deliver about the strain energy stored due to the bending in the case of a beam. You know that already we have done about the strain energy stored due to the axially loaded member. If the load is acting on an axially loaded member of length L and the load is capital P and the change in length is delta L, we know that the strain energy is capital U, that is equal to P square L divided by 2A into E, where capital E is the Young's modulus and A is the area of cross section of the beam, whether it is a rectangular or a square or a circular beam, and L is the length of the axial loaded member, and A is the cross sectional area in square millimeter or square centimeter or meter square. So that already we have dealt it. Now we are going to see about what will be the strain energy stored. So due to the bending, so bending is nothing but the bending moment is applied on the beam, whether it is a simply supported cantilever or the overhanging beam. So for example, I am taking a simply supported beam, the support A and B, and then subject to a point load of capital W, and the span is L. Since it is a constant load on the midspan, the reaction on either side will be of VA is equal to VB is equal to W by 2 in terms of kilonewton if the magnitude is given on the beam. And from that, you can arrive for the bending moment at a section from the left hand A, C and CB. I am taking the first portion as AC, which is at a distance small x from the left support. Now what is the bending moment at that section? The bending moment at the section MX is equal to, the reaction is W by 2 into X, so W by 2 into X. And what is the strain energy stored due to the point load in the case of a simply supported beam with a central point load? So therefore, the strain energy stored UAB is equal to the integral of 0 to X. So it is when X is equal to 0, the lower limit and upper limit is X is equal to L. So mx, mx squared divided by 2ei into dx integral. So where E is the fluxual rigidity of the beam in terms of kilonewton meter square or Newton into millimeter square, where W is in terms of kilonewton or the Newton. So if you integrate the corresponding value of mx, that is equal to integral 0 to L by 2. I am taking only first half because it is similar in the second half. You can multiply by 2. So 2 into integral of 0 to L by 2, yeah, the square of the bending moment. So bending moment, it is W by 2 into X square into dx divided by 2EI. So if you are integrating it, you will get the strain energy stored in the form of the corresponding EI and the load W into the deformation. Again, you know that the work done is equal to the strain energy stored. What is the work done in the case of a simply supported beam with the central point load? It is 0 plus W by 2. So that is the load into the deformation, WLQ by 48 EI. So which will occur at the midspan. So you are getting the strain energy stored is equal to the work done. Work done is half W into delta, half into W into delta is nothing but WLQ by 48 EI. So this is the strain energy stored in the case of simply supported beam with the central point load. Similarly, you can work out for any numerical problem. For example, if the load is say 50 kilonewton and the span is 4 meter, on either side AC and CB is equal to 2 meter, you can use these values, right? So load is 50 kilonewton, the reaction on either side will be 50 by 2, that is 25 kilonewton. So 25 into x, that is the moment at any section from the left hand side within the first half. So you can substitute the corresponding value of the Young's modulus. For example, Young's modulus of a RCC is 1.75 into 10 power 5 Newton per square millimeter, and I is the cross section of the beam is 300 mm by 500 mm. So that means I is equal to B d cube by 12. The breadth is 300. B into d cube is what? 500 cube by 12. You can put in terms of mm per 4. You substitute in the strain energy equation of, so you can get 0 to 2 meter 2 into, because the two values are equal on either side of the center of the load. So into mx square is 25 into x square divided by 2ei into dx. You substitute all the values, you will get in terms of kilonewton meter. You can convert to newton into meter or newton into millimeter. Again, the strain energy is also measured in terms of joules. So you know that 1 joule is equal to 1 Newton meter. So what would be the answer asked in terms of either SI unit, either in Newton meter or joule or kilonewton meter, you can produce the answer. So this is how the strain is stored due to a bending. So it is nothing but U is equal to integral of 0 to x into m square into dx by 2a. That is the main equation which you will use to find the strain energy stored. Thank you very much for patient listening. வாழ்க வையகம், வாழ்க வளமுடன். Thank you.